Okay, so we're going to talk about chemical equilibrium today. The first thing that we can do is we can highlight the important sections of the question. So the actual equation itself is going to be very important for us. And the mass of whatever we have, any figures we have usually are the important sections of the question. So go ahead and underline them. We can see we have 20.85 grams of phosphorus pentachloride. It was at 523 Kelvin. The temperature usually stays the exact same for these. So there's no reason to put that into our calculations at all. It's just there. And it says that it's in an 8-litre vessel. So the container that all of this reaction has taken place in is in an 8-litre vessel. So that reaction then comes to equilibrium at some point. And it was found that 80% of the original pentachloride, this reactant right here, has dissociated into these two products, but only 80% of it. Okay, so we have to figure out where is our starting point. So there's only really one way we can start here. We have a mass, we have a compound, so we can work out the number of moles that we have currently. So if I take the 20.85 grams of the pentachloride and divide it by the relative molecular mass of the pentachloride, you can find all of the information on the periodic table. Just go get the masses and you'll find that out to be 208.5. And mass divided by the relative molecular mass is going to give you the number of moles of that substance present. And it's in 8 litres. Okay, so another way of writing that is 0.1 moles per 8 litres. Now I'm just going to change all of my conversions straight away into moles per litre. So that's the amount of moles in 8 litres. So all we have to do to get it in 1 litre is divide that by 8, because there's 8 litres currently, and we'll get 0.125 moles per litre. Okay, so I have 0.0125 of this substance at the very start. Now we're told that it's disassociated a certain amount. So we have to work out how much this is disassociated by. And if it is disassociated by 80%, that means at equilibrium, 20% of the phosphorus pentachloride is at equilibrium. Okay, so I have 0.0125% or moles. That's basically at 100% before the reaction exists or starts. So if I get 20% of the amount of moles that were originally there, I'll find out how much pentachloride, the phosphorus pentachloride was there at equilibrium. So let's take 0.0125, the original amount, get 20% of it, and that will give us an answer of 0.0025 moles of our phosphorus pentachloride at equilibrium. Okay? So that's our first step. That's basically all that we could have done. We've only given one start point, the mass of the phosphorus pentachloride at the very start. So just following through with everything that I could do, every next step that I could do, you've found your way to how many moles of phosphorus pentachloride there are at equilibrium. Now we have to work out the rest. So we're going to set up a Rice chart. Okay, so scroll down here a tiny bit. So when you're doing a Rice chart, you just write R I, C, E, all the way down. And you write R is for your reaction, so you're going to write in your reaction, PCl5, and that went to PCl3, and chlorine, Cl2. Okay, now your initial concentration, I, we can write in here. So initially, we had 0.0125, this guy over here, moles of the phosphorus pentachloride. And initially, we had 0 moles of these two guys because the reaction hasn't started yet. Then, the phosphorus pentachloride has dissociated by a certain amount. We'll call that X. Okay, and if it dissociates by a certain amount, these form by a certain amount as well. Okay, and you can get the ratio based on your reactants. So see up here, we have a 1, and a 1. That's why these are all just 1X's. And there's a minus X just on the reactant side because that's dissociating, whereas the products are forming. So the products always get a plus and the reactants always get a minus. And the ratios are just 1, 1, 1. If the chlorine had a 2 in front of it, you would write in 2X there. But they don't, they all have 1. Okay, so that's that step. And then you write in your at equilibrium. So originally, our phosphorus chloride, pentachloride, was 100%. So just 1, we're going to leave it as 1. And it lost a certain amount, 1 minus X. Then over here, it was 0 plus X, which is just plus X, and 0 plus X, which is just plus X. Okay, so at equilibrium, you see we've lost a small bit of pentachloride, the phosphorus pentachloride, and we've gained these two compounds on the other side. And we've written them in the form of X. And we've stuck with the ratio of the reactants and everything, so that should be all good to go. That's your rice chart done. Now, what you can do is you can write in your information that you already have. Okay. Okay, so originally that 1 is 1 minus X. It's 0.0125 minus a certain amount, plus a certain amount, plus a certain amount. Okay. And now we know that at equilibrium, we have this amount of moles of the phosphorus pentachloride. Okay, so we can say that 0.0125 minus X equals, so that's the original amount of phosphorus pentachloride. It's dissociate a certain amount, and what's left over is the 20%, 0.0025. Okay, and then from doing that, you can work out that X gives you 0.01. So you found X. So now you can write in all of these. So at equilibrium, we have 0.0025 moles of that substance. We know X is 0.01. And we found all of the concentrations at equilibrium for this reaction. So we're ready to write our equilibrium constant. So I'm just going to wipe all of this now, and we can get a clear page to write our equilibrium constant. Okay, so we're going to take the products first. So we're going to write PCl3 and put them to the power of their coefficients, which happen to be 1 in this case. Okay, and we can fill in the concentrations now. And you should work out your equilibrium constant to be 0.04. Okay, so that's that one done. You found the equilibrium constant. So now you can take a look at the second one, pause if you want, and then try and give it a go. Set up your rice chart and continue on and finish it out. Okay, so hopefully you've done that now. Let's get into it. We can just go straight into reading it and figuring out what's the important sections. Okay, so we have our equation. Temperature again stays the same, as you can see. 1 mole of hydrogen, 1 mole of iodine. Okay, in a 1 litre flask. So we're given the moles of both reactants at this stage. And we're also given the equilibrium constant, 50. Okay, so we have to work out the concentrations this time. Okay, I'm just going to write down the important sections. 1 mole of hydrogen, or 1 mole of iodine. And it's at 1 litre already, so we don't need to divide it in like in the previous one that was 8 litres, so it's already in 1 mole per litre format. So we're just going to set up the rice chart. Remember, reactant, or R is for your reaction. Okay, and originally, the original concentration of 1 mole of hydrogen, 1 mole of iodine, and 0 moles of the hydrogen iodide, because at the very start of the reaction hasn't taken place yet. Okay, so both these are going to disassociate by the same amount, as it's a 1-to-1 ratio. There's no other numbers in front of them. So you're writing the change, sorry, C is the change, minus X, minus X. And then at equilibrium, it's going to be 1 minus X, or 1 minus X. Okay, this is going to increase by 2x because there's a 2 in front of the hydrogen iodide, and the change, that's the change. So 0 plus 2x is 2x. So you've finished your rice chart there. Now we need to put it into our equilibrium constant formula. So again, the products first, hydrogen iodide concentration to the power of the coefficient is now 2 this time. Iodine to the power of 1 and hydrogen to the power of 1. So put that in, Kc, and we see that the concentration at equilibrium for hydrogen iodide is 2x. And we're just going to square it. And the other two are 1 minus x to the power of 1, 1 minus x to the power of 1. Okay, we'll just simplify that down a tiny bit. 4x squared, and then 1 minus x times 1 minus x will end up to be 1 minus 2x plus x squared. Now we are given the chemical equilibrium constant already in the question, so we're not actually trying to find that this time, we're trying to find out the x value. So I'm going to let all of that, 4x squared, 1 minus 2x plus x squared, equal to the equilibrium constant. Okay, and with a bit of movement, you can then see that it is going to turn out to be a quadratic equation. So I'm going to wipe it out this now, and we're going to start our quadratic equation. Okay, so we're working with this. So I'm just going to clean it up a tiny bit more, get rid of the fraction, just drag things around about to make it look a tiny bit nicer for me. So it's going to be 4x squared equals 50 times everything on the bottom. Okay, continue on. Now it becomes 50 minus 100x plus 50x squared. Drag everything to one side and you will end up with 46x squared minus 100x plus 50 equals 0. So we're dragging everything across and simplified. Now, is there a number that we can divide across the line? There is 2. So if you divide the whole line by 2, just to simplify even further, you'll get 23x squared minus 50x plus 25 equals 0. Okay, now we're not going to go with the normal brackets factorization or magic number. We're going to have to go with the minus b formula, and this is in your log tables. Minus b plus or minus the square root b squared minus 4ac all over 2a, and your x equals that. So if you look here, we're going to drag out a, b, c. A equals to 23. B equals minus 50. And C equals 25. It's important to keep the signs as well and take your time when you're doing this, because most mistakes happen because somebody puts in everything into the calculator once, or they just forget to put the signs in, especially in this minus b section up here. They would leave it as minus 50 rather than minus 50. Okay, so just be careful with your signs. So let's fill that in now. So minus bracket, following along, minus 50 plus or minus 50 squared minus 4 times 23 times 25 all over 2 times 23, and that will give you your x. Okay, so we can change that first 50 into a positive 50, plus or minus. And if you put all of that into the calculator, you're going to end up with, we won't do that, we'll just do it section by section. Now if you put all of that, even the square root into the calculator, you will end up all of that changing into 14.14. So all of this section here, that will all change into plus or minus 14.14. Okay, and then divided by 2 times 23, 46. So then x equals 50 plus 14.14 over 46, or x equals 50 minus 14.14 over 46. Okay, and you get x equals 1.39 and x equals 0.78. Okay, so there's two answers. One of them is correct. And remember, originally we start off with 1 mole minus x. So x cannot be greater than 1, because that will give you a negative number for the amount that it is associated by. So you have to disregard that one. Okay. and we're going to choose x equals 0.78 as it's less than 1 as our answer. Okay, so that's our x value. So now we can calculate the final concentrations of each of the species that we have. So originally we had a rice chart. Let me just remind ourselves of what we wrote down for that. So we wrote down 1 minus x for the hydrogen, just associated by that amount, and so did iodine. H2, iodine, 2. And then we got 2 hydrogen iodide, and that was 2x. So now that we have the x value, we can figure out our concentrations. So 1 minus 0.78, 1 minus 0.78, 2 times 0.78, and this will get you all of the concentrations. So that'll be 0.22, 0.22, and 1.56 moles per litre. Okay, that's that question done. So now you can take a second and read this one, give it a go, and then I'll do it. Okay, so again, we're going to highlight reaction, 0.9 moles, 5 litre vessel, doesn't even give you the temperature this time. Okay, and we have a concentration at equilibrium. Write the chemical equilibrium expression for this reaction, and then find out what the actual value is. So the expression is easy enough to write out. It's just your products to the coefficients, to the power of their coefficients, over the reactants to the power of their coefficients. So what you write down for that is such. And that's your expression done. So the first two are to the power of 1, because there's a 1 in front of them in the reaction. And then the bromine chloride is to the power of 2. So that's the answer to the very first one. Now let's get on to the normal ones, the equilibrium constant for the reaction. So I'm just going to change the 9 moles in the 5 litre vessel to 1 litre vessel. So you're going to change that by dividing it by 5 to see how many moles will be in 1 litre. And we're going to get 0.18 moles of the bromine chloride in a litre. Okay. Now we should do that exact same thing for the other one, which is the chlorine, because that's still in 5 litres. So you're going to go 0.4 divided by 5, and that will get you 0.08 moles of chlorine in a litre. Okay, so that's all converted down. Okay, let's do our rice chart. So again, we write out the reaction. The initial concentrations that we've now changed. So the original is 0.18. This would be 0 and 0. It's going to change by a certain amount. Now you can do this as minus x and then minus half x plus half x plus half x if you want. Or you can just stick with the number in front of the compound. So there's a 2 in front of bromine here, bromine chloride. So you can just put in a minus 2x there. The change would be plus x over here because there's 1s in front of bromine and chlorine. Okay, so that's going to change at equilibrium to be 0.18 minus the change, 0 plus the change, which would be plus x, and the same thing over here. So your rice chart is done. And we do have the amount of moles of chlorine at equilibrium, which is here. So plus x. We've already worked that out up here, 0.08. So x equals 0.08. So I already know what x is. So if we work out the concentrations, that means that's 0.08. This is 0.08. And then you need to work this out, 0.18 minus 2 times 0.08, which will get you 0.02. So if we put them all into our equilibrium constant, the concentration of the bromine, the power of 1, of chlorine, and of bromine chloride to the power of 2, because its coefficient is 2, you'll get an answer of 16. And that's that one done. This is an actual leave insert question now. So again, you can pause, give it a go, and then I'll do it out. Okay. So we have nitrogen, hydrogen forming ammonia. Okay. You don't have to worry about the 3 different pressures. There is theoretical questions there as well, and I've just taken that part out to focus on the calculation side of it. So we have 9 moles of nitrogen, 27 moles of hydrogen, and in a 10-litre container. 6 moles are present at equilibrium at temperature T. Write out the chemical equilibrium constant for the reaction above. Okay, so you should know that that's the products, concentration of the product, over the coefficient, to the power of the coefficient, over the concentration of the reactants, to the power of their coefficients. Now, okay, that's the first one done. Calculate the value of Kc under these conditions. Okay, so I'm going to just change all of those moles per litre, moles in the 10 litres into moles per litre. So let's go with the nitrogen first. That was 9 moles. And it was in 10 litres. So that's going to be 0.9 per litre. Hydrogen, 2.7 moles per litre. And ammonia, NH3, 6 in the 10 litres. So it's going to be 0.6 moles per litre. That's just done now. Okay. So now we can do the rice chart. So we have our reaction. Our initial concentrations. The change. So again, there's a 1 in front of it, so we're just going to go minus x minus 3x. And gains 2x. So you're just looking at the numbers in front of the compounds in the reaction to get those. And then the minuses always go with the reactants, plus always goes with the product. Okay, so at equilibrium then, 0.9 minus x, 2.7 minus 3x, and then 0 plus 2x, which is just 2x. So they're the concentrations at equilibrium. So we know how much ammonia was produced at equilibrium. It's 0.6. So let's go with 0.6. The concentration at equilibrium equals the 2x, because that is the concentration at equilibrium. And then you can work out x to be 0.3. Okay, so that means this is 0.6. 0.9 minus 0.3 is 0.6. 2.7 minus 3 times 0.3 is 1.8. And you have all the concentrations now at equilibrium. So you can put them into your equilibrium constant reaction. So 0.6 squared over 0.6 to the power of 1, 1.8 to the power of 3. Okay, and you'll work that all out to be 0.102 for your equilibrium constant. Next part then, we wipe this all out. On this side, at least anyway. It says find the percentage by volume of NH3 in the container at equilibrium. So we know there's 0.6 moles per litre of NH3 ammonia at equilibrium in the vessel. How much is that compared to the rest of it is basically what it's asking. So we have in the whole container 0.6 moles of ammonia, 0.6 moles of nitrogen, 1.8 moles of the hydrogen, and I'm just going to compare the ammonia compared to all of the vessel. That's it. Multiply it by 100 to get a percentage, and you will work that out to be 20%. That's your answer to all them.